Good morning, everyone. Hey, good morning. Thanks for coming for my session. So my personal relationship with cloud automation started about 2 years ago when we were moving a bunch of applications from on-premises to Azure Cloud. And for one larger application, we sort of decided to do it all perfectly well and all best practices. And we automated everything from zero to live application in Azure, just one button click. And that's amazing that you can do this, but just to automate cloud infrastructure, we had to write, so we used ARM templates, Azure ARM templates, and we had to write like 4,000 or 5,000 lines of JSON, which described all our infrastructure. It's like the application is no big deal, it's just web servers, databases, queues, nothing super special. But it's still thousands of lines of JSON, which is pretty unreadable and completely unwritable, to my opinion. So I thought back then, okay, there must be a better way to do this, and probably tools will evolve very fast after this, so I should watch the space. So that's how I got here. So the plan for this session is twofold. In the first part, I'm going to explain a little bit about cloud automation and infrastructure as code, why you should do this. In the second part, I should make a case for using general purpose programming languages, as TypeScript in the title, but also others, to automate your cloud infrastructure. Okay? So I start with on-premises. Probably many of you still run applications on-premises together with the cloud or exclusively. So a typical scenario, having a web application, you probably have several servers for your web layer, your databases, some networking gear, and this is all managed by an IT department. They have to buy servers, install operation systems, patches, install your IaaS or whatnot, Nginx, databases, and then your applications. Hopefully some level of automation, scripting, and so on, but still a lot of manual work. And you probably have multiple environments for your application. Your production, maybe staging, which is one-to-one copy of production, maybe smaller environments for testing, development, and so on. And all of them have to be supported by human beings. And the servers live for years, so over time, a lot of manual work leads to small differences in the servers. Every server has a name. Everybody knows them by name. There is a guy always who is responsible for this server and another guy for another server. They're sort of unique things. It would be a big deal to just destroy all of them and create new ones. That probably is not really feasible because nobody really remembers how you got there. So long before cloud automation, people realized that's a problem if you have a lot of servers to manage. So they created tools for configuration management, like Puppet and Chef. And the idea is that you describe your configuration of the server as one machine readable file, okay? Configuration file or program. And then there is a tool who knows how to read this file and apply it to your server and install all the software and patches and stuff like that. And that basically means that everything is automated. If you need 5 servers, which are exactly the same, you put this file on 5 servers, you install an engine, and engine will take care of configuring the server. So that scales much better. And the benefits are numerous. First is repeatability, as I said, but you also get documentation about your environment, like the best kind of documentation which never lies. It's actual truth which applies to servers. It's never out of date. You can put it to Git, track changes over time, see who changed what, why, when, and so on. Because it's automated, you trust it more, it's more safe, so you tend to make changes faster, iterate faster, be more agile. And you can also reuse parts of your files, like you can find them online from somebody else, you can share it with other teams in your company, and so on. So you reuse them more. And finally, last but not least, because of this sense of autonomy and everything is in your hands, people tend to be more happy using these tools. And I think this is a factor which is underestimated a lot of the time. Like, you should be able to feel happy with the tools that you use. If you're not happy, you're not going to use them to full extent. That's a big factor when you select something, in my opinion. Now to the cloud. So cloud brings on top of configuring the servers. Now you can create your servers on demand just with API calls. And not just servers, but also databases, queues, Kubernetes clusters, managed services, machine learning, whatever. Really amazing stuff. So every cloud, this picture is for Azure, but every cloud has a layer to manage your services. So they provide management API, which is just a REST API at some point. And then to create any service, you talk to the same API, you ask for a virtual machine or web application or a queue or something. And then whatever client you use to create this infrastructure, be it the portal in the browser, be it CLI, be it your SDK or third-party tool, they all in the end talk to this API to provision infrastructure. Okay, so the lowest possible level to do this is just to call these endpoints directly. You can craft your HTTP request with all the proper fields, send it and get a resource back. But that's too low level, like nobody wants to do this manually. So every cloud also has a set of SDKs for most popular languages, TypeScript, Java, Node.js, Python, .NET, Java, whatever. So you can write code, and then this code is directly translated by them to the HTTP calls. Also, if you are more from operational background, you like your CLIs, bash scripts, PowerShells, you can automate infrastructure provisioning with CLI commands. So one way to create your infrastructure is just to write a big script, run it, and get it, which works, but has its downsides. First, it's very imperative, so you have to describe step by step in order what to do in order to get there, like to figure out dependencies in your head and make the right sequence of commands. It's fine when you just create your infrastructure for the first time, but then if you live with it for months and years, you have to write a lot of update scripts from state n to state n+2, n+1. Like, it gets complicated. Different environments are in different state. Error handling is very hard. If your script fails in the middle, you most often don't know what exactly happened and like what's the current state of your environment, where you should restart. You did not test this failure before, so you don't know if you run it again, is it going to be idempotent? Is it going to work through the end, or is it going to create duplicate resources, for example? So it's still low level. As I described, the configuration management tool used the idea of desired state configuration. You describe the end goal. So the same principle applies to the cloud. You can say, I want to describe my target state, whatever it is. And then there is a tool which knows how to compare this target state with current state of your environment in the cloud. And then the tool will figure out all the steps to go from current state to target state. And you just don't care about the current situation too much. So if we zoom in a little bit, both current state and target state can be represented as a graph of resources. So every node here is a resource in Azure or AWS, and edges or arrows are dependencies. That's very important. Some resources depend on the other, so the proper creation order will depend on the sequence of those graph, direction of that graph edges. So whatever tool you pick, it should be good in two ways. It should be expressive enough for you to describe your target configuration correctly, ideally. And then it should be good at comparing target with current and applying all the changes. The challenges here for such a tool, and it's still work in progress, nobody is perfect, no tool is perfect yet. So it has to be expressive. You should write as little code as possible and make as little mistake as possible. It should automatically, ideally, track all the dependencies and make the plans with these dependencies in mind. That gets tricky, especially when you need to replace a resource. So the notion of immutable infrastructure, when you don't change your servers these days, but when you need a major change, you just delete the old instance and create a new one. But what if 5 other resources depend on it? Like, what's the proper way to migrate this, ideally without downtime? And the third challenge is to be transparent about what it's about to do. So no tool is perfect, so ideally before changing your production environment, you want to see what the tool is going to make. Is it going to destroy my precious database while doing so because it thinks something changed there? So it should be transparent about what it will do before it actually starts doing, and you should be able to test this in advance. So every cloud, doesn't matter what you work with, has their own desired state configuration tool. So AWS has CloudFormation, Azure Resource Manager, Google Deployment Manager. They are sort of the same thing on high level. And they are also similar in a way that they use markup languages to define your infrastructure. As I said, we used Azure Resource Manager with JSON files, so that's a very small example, but you define an array of resources as JSON nodes, objects. And then you just define resource types, names, thank you, and some properties. And mostly what the tool does is it can convert this JSON file to a set of calls to the HTTP endpoint that I discussed before, and just puts the properties into the body and sends them in order, and that's about it. So it's about the same level of abstraction as they call in HTTP endpoints directly. So CloudFormation for AWS is very similar. They started with JSON, then they moved to YAML mostly. Doesn't really matter. You still write text files with a lot of layers there, and you use some specific language to define dependencies and whatnot. Google has YAML as well, so I don't have a slide for that, but it's mostly the same thing. All these tools have some challenges. Well, first, they are specific to the cloud that you choose. If you're using AWS for 2 years, you're good with it. You go to Azure, your skills are almost zero because they are very specific to the cloud that you are using. Then also because they are such fundamental services, they describe all the possibilities. They never can make breaking changes because they will break a lot of customers. They tend to be very low level and rigid. They are averse to change anything. Like these tools exist for years and they don't change that much. So they are not the most pleasant experience to work with. And also they are closed, so you cannot really see the code, you cannot influence them. You can just complain to Microsoft, for example, and then good luck with that. So there are alternatives. For example, a very popular one is Terraform from Harsha Corp. So they reinvented the whole stack. The goal is the same, but they use their own technology for everything to provision cloud infrastructure. So they invented their own language called HCL, Harsha Corp Configuration Language, which is still markup, but it's in the end it's much more lightweight than JSON or YAML. Well, maybe not much, just more lightweight. And it has good constructs for defining dependencies. For example, instead of just saying a string in JSON, you would refer to a resource, like in this example, by type, name, and then its property. And then that's enough to define dependencies between two resources. So that's good. Another great possibility is that the same tool works for multiple clouds, AWS, Azure, GCP, but also it works for different tools like Kafka or Kubernetes or monitoring tools or some databases. So the vision is that you can define your complete infrastructure in one set of configuration files. So let's say Azure Kubernetes cluster and then some Kubernetes deployment objects and some maybe monitoring from New Relic in the same set of templates, which is quite powerful. But markup is still markup, and it has its own challenges. First, the tooling. Like we are developers, we are used to all the IDEs and nice stuff that comes with it. You don't get this with JSON. Well, they try to create their own plugins for VS Code and whatnot, which kind of automates something, but it's still far from the same experience that we are used to. Discovery is a big problem. When you start typing, it's virtually impossible to just sit down and type your resource. You probably need to find it somewhere online, copy-paste it, or go to the portal, create a resource, and copy-paste what's there. So it's really a lot of copy-pasting going on there. And finally, because it's all low level, there is no way to create abstractions of your own, or no good way. The size of the result in templates tends to be huge, thousands of lines of code. So I had this very simple example where I created an application like URL shortening applications, bit.ly or tinyurl.com, very simple one. So you go to your website with plus shortcode, and then it redirects you to the full URL. It takes literally 20 lines of JavaScript to implement this with AWS Lambdas. You just get HTTP request and then redirect it to proper URL from the database. But to define all the infrastructure that's needed to deploy this, it's an order of magnitude more lines, and it doesn't matter if it's AWS or Azure or even Terraform. So it really doesn't feel right. You write just several lines of code, and then to deploy this reliably and all the benefits of infrastructure as code, you have to write hundreds of lines of code. Also, these markup languages, they are not just JSON or YAML. They have languages embedded into the language because they need to express things which are not expressible with native JSON. For example, this is AWS CloudFormation references. To define the dependencies between your resources, they have a special construct with ref and then the name of the other node in JSON, and that will be specially interpreted by CloudFormation as a reference to that resource. They have conditionals, like in Azure, for example. Sometimes you don't want to deploy a resource in one environment, for example, in test lab. So you can say condition and then use special syntax with square brackets and the equals function to define that you don't want to deploy this resource if the parameter is no. They have loops. Also, Terraform, you can kind of define your local collection array of files in this case. And then there is a special attribute count, which refers to the length of that thing. And then count index will give you the iteration index. So it's kind of a for loop, but in their markup language. So they reinvent all the constructs that we already have in the languages. Another big challenge is reusability. As I said, like there is no good way to create abstractions on top of this markup languages. Terraform has modules, but they are not really great. It's hard to use the same set of templates for multiple environments when the environments are different. So you end up writing those conditionals, and that just sucks. There is no thing like package manager, so you have to distribute your templates either manually or put it in something like S3 buckets and so on. Testing. There is basically no testing. You just deploy your template and then you see what you got. Ideally, we would like to test it on multiple levels. Like we could test before deploying, we could test some properties of resources that are about to be created. We could inspect the graph of resources to understand if we are doing something wrong, if we have like orphaned resources or something, and testing after deployment. So when I look at this list, I think to myself, we solved all of these problems many years ago. Why do we have to solve them again? We developers have all these amazing tools like IDEs and code completion and compile time check, version checking, correctness checking, and package managers, and refactoring and whatnot, and this all works. So why cannot we use the same tools for cloud infrastructure? So there are several tools that aim to achieve these goals. I'm going to mention two today. One is Polymer, one is AWS CDK. They are sort of comparable. I'm a contributor to Polymer, so I know it much better than CDK. So most of my examples are for Polymer, but they are sort of applicable to both. I will explain the difference later on. So Polymer is open source tool. It's free to use. You can download it and run it on your machine. You can think of this as Terraform, but one important difference is that you use general purpose programming languages to define your infrastructure. So at the moment you can do JavaScript, TypeScript, Python, Go, and C#, F# VB being launched like this week. So program looks just as a TypeScript application, for example. You write code, you instantiate new objects to create resources. So in this simple example, I have two resources, a resource group in Azure with a name, and then I use this variable in the definition of storage account, and that automatically creates dependencies between them. So when it's time to deploy, the program will know to first create a resource group and then a storage account. Slightly more complicated example for my URL shortener. I can now define all the code in like one screen of code. I have three objects here. The top one defines DynamoDB table. Then this DynamoDB table is used to define a Lambda function. You can see that I pass counter table name to environment variable. And then the third statement is creating an API gateway. So like HTTP proxy in front of Lambda if you don't know AWS. And again, Lambda is used as a parameter so that they are all connected to each other. And these are high-level components. They use a lot of defaults. If you know how API gateway works, you have to configure like a lot of configuration to make this work. But they take like sensible defaults. You can always go on the lower level if you need to configure those. But you can also start with high-level controls. That's your choice. Now, a very important thing that you may not immediately understand is that this is still desired state configuration. So the program doesn't describe the steps to run when you execute it. It describes the graph of resources that you want to create. So maybe I can explain it with this diagram. You have a language host which knows how to read TypeScript, but it doesn't immediately call AWS or Azure or anything. It just compiles the program and builds a graph of resources, of resource definitions with properties. Then it sends this graph to the engine, the CLI. CLI is required in order to deploy your application because that's all the brains of the deployment. And it compares this graph to the current state in your cloud environment. And then, based on this comparison, it is able to figure out the exact steps to run. So if you have current state exactly the same as your definition, it will do nothing. If you miss one resource, it will create one create command for AWS. And then there are providers or plugins for different clouds or whatnot. So it's the same concept as Terraform. There are plugins for most major clouds. Actually, you can take any Terraform provider and make it a Polymer provider. So it's just the same list of possible destinations for your code. So you can write code with AWS and Azure in the same program if you want to. Not sure why, but you can. You can define your Kubernetes deployments on top of cloud and so on. So what are the benefits of real code? Well, you don't have to learn any new languages. You just use the language that you are hopefully used to, if it's in the list before that. You use package managers. You still use the same compilers, linters, IntelliSense, whatnot. You can also use other libraries that you find fit. I will give an example later. Do conditionals, loops, components, classes, functions. And a very powerful one is that you can create your own abstractions. So if some high-level component makes sense in multiple places in your infrastructure or for multiple teams in your company, you can create your own component and then distribute it as an NPM package or NuGet package. And then everybody can benefit from this. So some examples, you open Visual Studio Code, you start typing, you immediately get IntelliSense or code completion. You get documentation in the pop-up. If you mistype something or you miss a required property, you will get red squigglies immediately. So feedback is very fast. You don't have to run the deployment to see this. You just see it immediately in your editor. Conditionals loops, so a very common case is, for example, you want to deploy an EC2 instance to every availability zone of a region in AWS. So the problem is that every region has its own set of availability zones. Some have 2, some have 5. So you don't really know in advance. You have to hard code it in your template per region in this case. But if it's just a general programming language, you can call AWS SDK to get a list of availability zones and then just make a for loop to create an EC2 instance in each one of them. And when it runs, it will just call to AWS, get 3 instances, and then create 3 EC2 instances. As simple as that. An example of components, so in order to produce an Azure Kubernetes cluster, you need to set up Active Directory and applications and principals and virtual networks and subnets in the cluster itself. If you don't want to care about this too much, you can create a component which does all the sensible defaults for you, maybe exposes some parameters to configure. And then this is a component and you can give it to your friend and he will just create an AKS cluster by filling just a couple of properties with names or subnets and so on. So another product, as I said, is AWS CDK. So that's the product by AWS themselves. It's specific to AWS, obviously. You cannot use it for Azure. But the idea is similar, that you use general purpose programming languages like TypeScript, Python, Java, and .NET. And then the implementation is a bit different because they generate CloudFormation templates from that code. So you run the code and you get CloudFormation YAML as an output. And then the deployment pipeline is the same as for CloudFormation. So this has both downsides and upsides. Like you get all the problems of CloudFormation except writing it manually. But you also get all the benefits as supported by vendor and rock solid and so on. So I guess the heuristic is if you are on AWS and you don't need any other providers like Kubernetes or Kafka or whatnot, it's fine to start with CDK. It's probably like the vendor tool to be used in the coming years. If you need something else, then start with Polymer. Code-wise, it's very similar. Like you write new objects. Well, API is slightly different because it's a different implementation, but it's the same idea of high-level components that then you can link with variables and loops and whatnot. So I explained a lot about why I think it's a good way to define infrastructure. Some people are really scared to give their developers such a powerful tool. They say, oh, they're going to make a mess out of it. They will shoot themselves in the foot. They will create horrible things. We don't want to give them powerful tools. Well, I don't know for sure, but it doesn't feel right to me. Like limiting your developers by giving them worse tools, it doesn't feel like the good way to make sure they do the right thing. So every cloud has guardrails, like policies. If you are an operation guy for the company, you can always define a policy to prevent people from doing any things that you think are stupid. So that's, I think, a better way to like govern your developers and then give them the best tool that they want. But I don't know, maybe I'm wrong. I think the bigger thing here by using general purpose languages is that you go from infrastructure as code to architecture as code. So when you reason about your programs, you usually can draw diagrams like this. So I want to run my container every 1 minute, so I draw timer and arrow with pointing to ECS instance. And then when I go from this to code, I think on the same level of abstraction. I have an object which has two properties. One is schedule, run every minute, and the other one is pointing to the container in the registry. So it's easy to go from this to this in your head. Another example. I have two buckets in S3. When something drops into the bucket, a report, I want to pre-process it, zip it up, and put it into another bucket. So I draw this diagram with two buckets, and files go in and out. And then I can write the code, which is on the same level of abstraction. I define two buckets in 2 lines. I give them names. And then I can link them to Lambda, as I showed before, or even, that's also a feature, you can write the code right inside your infrastructure definition. So you can say, that's just a general purpose programming language, so you can use callbacks and whatnot. So you can say, as in your, for example, Express application in Node, or in your browser application, you can say on object created and then pass a callback, and then go for the objects that you got, zip them up, use AWS SDK to upload them. And the tool will take care of serializing this callback, making it a zip file, uploading all the dependencies to AWS, linking it to a proper bucket, doing all the low-level stuff while you write code, which is very natural for developers. You can also create abstractions of your own. So, example from my practice. Say I'm working on an e-commerce site which has customers all around the world. So I want to be deploying my application to multiple regions, multiple locations. I can use Cosmos DB to distribute my data automatically. That's a smaller problem. I just define multiple regions. But then I need to put my compute application to every region, that I want to target same regions as Cosmos DB. So I copy my infrastructure n times. And then I have some front-end service which knows how to route my users to the nearest location. And that's all possible in Azure, but you can see how it becomes quite complicated to define this infrastructure correctly, to link the proper regions together and make the routing and so on. And maybe another team in my project, they actually want more or less the same, but they don't use function apps, but they use container instances because that's what they chose. But for the rest, it's the same pattern. They still need Cosmos DB, they still need traffic manager in front. They just need different compute layer. So we can talk to each other and agree to create a component which abstracts this away. So we would create a component which creates Cosmos DB and front-end routing, but makes pluggable slot for the application infrastructure. And then once this component is created and tested, everybody can use it. For example, I can use it for my functions to just call a new Cosmos app, give it a list of regions to deploy it. And then the second step, I apply my developer skills, known patterns, factories. I give it a factory which accepts location as a parameter, and then it creates just my function app in one region and returns its ID so that it could be linked to the front-end routing. And I can do containers here, I can run a Kubernetes cluster here, I can run VM scale sets. The component doesn't care, so I separated the concern of geo-distribution from the concern of creating my application infrastructure, which is very powerful in my opinion. So I still have 8 minutes, so I want to jump to a quick demo of what it looks like to deploy the real code. Well, not real, just example. So I can switch my screens. You should see, yes. Collapse this. That's not the right example. This is the right example. Readable on the back? Okay, perfect. So that's a simple program for AWS. It's a TypeScript, as promised my title. So I import 2 libraries from Polymer, AWS and the generic one, but I also can import any other libraries, in this case, MIME and Node.dir. They just help our utilities functions in Node.js, if you don't know. Then I start defining my resources. I create well, the purpose of this program is to create a static website on AWS, which is quite simple. I create an S3 bucket, which is like a storage for files. I give it a name, and then I say what's the root document should be. And then I use the existing libraries to iterate through my folder on the disk, which is here. It has 2 files right now, which I want to deploy. And then for every file, I can also use things like substrings or any language feature that I want to. And then I call MIME getType to understand what kind of type it is. In my example, it's HTML, could be images, CSS, and so on. And then for every file, I create a bucket object. And you can see that I get all the tooltips and IntelliSense and so on. So there is a loop which creates objects, and then in the end, I can export the endpoint because it's not known in advance, or at least I don't know it. I can export the endpoint of my website to the output of the program. So now I can switch to the CLI, if I find it, yes. So that's the same folder where my program is. Then I can type Polymer app. First it will give me a preview of what's about to happen. Yes, so it says there is a stack, which is like a container for my application. There is 1 bucket, and it found 2 files, 404 and index, and it's going to create 2 objects. So if I'm happy with this, I can say yes. If I'm not happy, I say no, and then nothing happened, because again, it was just a description of desired state. It didn't do any operations yet. So now it actually goes, and the engine applies my changes to the actual environment, and several seconds after, I can see that I have my endpoint printed out, and I can copy this to browser. If I find browser, yes. And I should have it up and running. So that's the process of deploying. I can show you a more real-world application, I guess. So this one deploys Azure Kubernetes cluster, and then it deploys several services in this cluster, and uses several managed services. So I'm not going to run this because it will take like half an hour to deploy, but I'll just we'll walk you through this. A typical approach is to split your larger applications into multiple layers. So in this case, it made sense to define Azure AD identities on the lowest level, then some managed infrastructures yeah, I'll just show you. So the first layer defines roles and permissions and everything that's needed for deploying a Kubernetes cluster. Then the second step defines virtual networks, subnets, login solutions, and so on. Now the third step creates the Kubernetes cluster itself. So somewhere here, it will call Kubernetes cluster. And the cool thing is that you can use outputs of previous steps in the next step. So they are all linked together and they all depend on each other in the correct order. So on top of Kubernetes, I can start deploying my application. So first I can deploy like analytics plugin, and then, yeah, that's pretty boring. And then I can combine managed infrastructure like Cosmos DB, I'll collapse this, like Cosmos DB accounts to provide storage for my stateless Kubernetes applications. So I defined Cosmos in this step, and the last step would be deploying a Helm chart, which does some Nginx and so on with Mongo secrets. So even if you don't know about Kubernetes, and that was a very fast demo from my side, you see that you can structure your application in a good way, in a way that makes sense to you, and also mix and match managed resources of your cloud provider with some third-party resources like Kubernetes or Kafka. Okay, I think it's time to wrap up. Just a couple minutes left. The conclusions, what I want you to bring from this session. First, if you are developing cloud applications, please don't go to the portal and click, create your application done. That works for demos, but it doesn't work for real application. You will say thank you to me if you start using infrastructure as code. Pick the tool that you like, either a native code tool from your cloud provider, or Terraform, or Polymer, or CDK. Use something. On a historic perspective, we see that our applications start to be composed from smaller and smaller components over time. So we had servers, virtual machines, containers, microservices, serverless functions, less and less. The smaller the components become, the more of them you need, the more complex the deployments become. And so you need better and better tools to automate all of that. And once you get better tools, you feel more comfortable to go even further and create more components and smaller components and create abstractions on top of them. So I think that's like a loop which goes on, and the loops will just push the tooling to become better and better. It's quite likely that in 5 years we're not going to use any of those tools that we use today, and something new will appear. But my advice, treat infrastructure as part of your application. If you're a developer, use the existing skills to program it. And that drives me towards using TypeScript or other general purpose languages to define my infrastructure in the same repository, in the same way where my application lives. And with this, thank you so much for coming. I'll be here the whole day. If you have questions, we can discuss all of that. Thank you.